Hey folks, this is Mrs. Abbott here, giving you a little tutorial on pH. I just want to make sure that you guys follow along with your pH notes, which can be accessed through Schoology, just to help you better understand this. A little background before we begin with pH, which many of you have probably heard of, and it has to do with our friend the water molecule over there, over here on the right. Um, Water tends to break apart into a hydrogen ion and an OH ion, called the hydroxide ion, every once in a while. In pure water, which is really hard to find, you have the same number of dissociated H plus ions or hydroxide ions and hydronium ions. So only about one water molecule in every 554 million is actually dissociated like this. And this is kind of a picture of what a dissociated water molecule looks like. Here's the normal water molecule. Here's one that's broken apart into a hydrogen ion and a hydroxide ion. First, let's talk a little bit about the hydrogen ion. Remember, hydrogen looks like this over here. It's got a proton and it's got an electron and no neutron. Well, hydrogen atoms tend to give away their electron when they are in a tug of war with another molecule or atom. So a hydrogen ion is just basically a hydrogen atom that's lost its electron, and now it's just a proton. So here's a picture of it. It's a proton, no electron. So it now has a positive charge, because remember what we learned about ions. If you give rid of your electron, you're positive. And sometimes they're just referred to as protons. Hydrogen ions really are just a proton. And when dissolved in water, acids, which we'll learn a little bit more about later, those are things that are low in the pH scale, tend to donate hydrogen ions to the water. So acids have a lot of extra hydrogen ions or protons. Hydroxide ions are basically what's left of a water molecule when the hydrogen leaves. So here's a picture of it here. And they're a hydrogen and oxygen, but they stole that electron, or stole it. They kept that electron that the hydrogen left behind, so they take on a negative charge. And bases tend to be mixtures that have a lot of excess hydroxide ions. So hydrogen ions are basically the ear of the Mickey Mouse molecule that got left behind, and it sort of said, you know what, you can keep that electron we've been tugging with, and it is positively charged and hydroxide ions are negatively charged. If a solution has a high concentration of hydrogen ions, then it's acidic, and if a solution has a high concentration of OH ions, then it's basic. So this is kind of like if the solution has a bunch of these molecules here, or more of these than hydrogen ions, then it's a base. If it's more hydrogen ions than hydroxide ions, then it's a low pH and it's acidic. One of the classic acids that we'll use in our class is hydrochloric acid, which splits up and tends to dissociate into hydrogen ions and chloride ions. And another well-known one is sodium hydroxide, and sodium hydroxide tends to split up and have a sodium ion and a hydroxide ion. And if you look at this picture here, here's a hydrogen molecule. Remember, it dissociates into H pluses and OHs. Hydrochloric acid dissociates into those two molecules, and sodium hydroxide dissociates into those. And if you were to put both hydrochloric acid and sodium hydroxide into a container of water, they tend to cancel each other out. So hydrogen chloride, sodium hydroxide, they cancel each other out. The excess H's here tend to find those OHs there and say, hey, my long lost friend, let's make some water. And so what you get is water and salt, because this chloride is negative and this sodium is positive, and they want to form an ionic compound. The hydrogen ions of the acid join with and are neutralized by the OH ions of the base, and they form water, which is pretty neutral. So now this solution has salt in it and water in it, but it's not necessarily an acid or a base. So here's just a quick animation I found that I thought might help us out here. So, a little TED Talk action.
Acids and bases are everywhere. They're used to make foods, soaps and detergents, fertilizers, explosives, dyes, plastics, pesticides, even paper. Our stomachs are very acidic. Our blood is slightly basic. Our proteins are made up of amino acids, and the letters in our genetic code, those A's, T's, C's, and G's, are all bases. You were probably taught how acids and bases behave on the molecular level. You were probably never taught that a long time ago, like ancient Greek ago, before anyone knew about atoms or molecules, acids and bases were defined by how they behaved. Acids tasted sour and corroded metal. Bases felt slippery and could somehow counteract acids. When molecules dissolved in water interact, they're exchanging two main currencies with their surroundings: protons, also known as hydrogen ions, and electrons. Depending on how a molecule is composed or shaped, it may be willing to donate or accept either protons or electrons with some other community member. And some molecules are far more aggressive than others when it comes to donating or accepting either currency. Remember that protons are positively charged and electrons are negatively charged. So if a molecule is willing to give up a proton, that's not too different from it being willing to accept an electron. Either way, it's becoming more negatively charged. Other molecules are willing to accept a proton or give up an electron. These are becoming more positively charged. Some substances are so aggressive about donating their protons that when they get a chance, all of the molecules in a sample will dump a proton, sometimes more than one, to the surrounding water molecules. We call these strong acids. Meanwhile, some compounds are so ready to accept a proton that they won't wait around. They'll just rip one off water, which usually has two protons but is generous enough to hang out with just one. We call these strong bases. Other acids and bases are not so strong. They may donate just a few of their protons to water, or accept just a few protons from water, but most of their molecules stay exactly the same. If left alone in water, they'll reach some equilibrium point, where maybe only 1 out of 100 or 1 out of 10,000 of their molecules has exchanged currency with water. As you might guess, we label these acids and bases weak, but in the common sense of the word, they're not weak. The vinegar in your salad dressing that you can smell from across the room, that is a weak acid. The ammonia you spray on glass for a streak-free shine, that is a weak base. So it doesn't take much to be an active player in the chemical economy. Most acid-base chemistry takes place in water, which can act as either an acid or a base, accepting deposits and enabling withdrawals like a 24-hour molecular ATM. And when a proton deposit customer, that's an acid, and a proton withdrawal customer, base, shop at the same time, their net effects on water's account may cancel out, and we call this neutralization. Now, certain molecules can behave as acids or bases without water, but that's another story. Let's end by saluting water as the resilient and fair banker for acids and bases. It's always open for business, doesn't charge interest, and will never foreclose on your molecules, which is more than I can say for.
Okay, so going back to our slide, hopefully that helped you understand a little bit more about what we were talking about. Next thing I want to talk about are buffers. Buffers, and I apologize for putting all of this up at once. I'm usually animating things. Those are just compounds that tend to neutralize the pH of a solution. And what they do is they're sort of these magical compounds that are able to either donate hydrogen ions or hydroxide ions to keep a solution neutral. And they play a really important role in most organisms because a lot of organisms need to maintain homeostasis, and that includes maintaining a pretty specific pH. If our blood gets any more acidic than 7.35, you can, get acidosis and die. And if it gets any higher than 7.45, you can get alkalosis and eventually die. So just to show another animation that has to do with buffers and their importance.
Many chemical substances in body fluids dissociate and give rise to free hydrogen ions. The pH scale is used to measure the concentration of hydrogen ions in solution. The normal blood pH values vary around 7.4. When hydrogen ion concentration increases, the pH value decreases, resulting in a state of acidosis. Conversely, when hydrogen ion concentration decreases, the pH value increases, resulting in a state of alkalosis. Life-sustaining chemical reactions are catalyzed by enzymes, which can only function effectively within narrow pH ranges.
So as you can see, our blood is a classic example of something that needs to be at a pretty stable pH or things will go awry. pH is a pH scale is a logarithmic scale, and what that means is that every step in the scale represents a multiplication of 10. The scale goes from 1 to 14, and you can see some of the common objects that we're used to seeing in life. If we have a solution where 1 out of every 10 molecules is a dissociated hydrogen ion, then we refer to that concentration as 1/10 or 1.0 times 10 to the negative 1, and that would give us a pH of 1. This is how it works. So if the pH of a solution decreases by 1 pH unit, that would represent a 10-fold increase in the concentration of hydrogen ions. For example, lemon juice has a pH of 2. That means that 1 in every 100 molecules in the concentration are hydrogen ions. This is 10 times more acidic than orange juice, which has a pH of 3, which is 1 in 1,000 hydrogen ions in concentration, or 1.0 times 10 to the negative third. So how do we decide if something is an acid, a base, or neutral? Well, if the pH is 1.0 times 10 to the negative 7th, then it's neutral. If it's higher than that, so if the concentration is bigger than 1 in 10 million, the pH is acidic, and if it's smaller than that, then the hydrogen ion concentration, then it's a base. The pOH is the negative log of the concentration of OH ions, so the pOH and the pH is always going to be equal to 4. So if you have here's something that's very basic. If you have a high concentration of OH molecules, so 1 in 10 is an OH molecule, but 1 in many zeros later is the hydrogen ion concentration, then they both are always going to add to 4. So cola down here has, I said it had a pH of 2, but it has a pH of, let's say it's lemon juice. It has a pH of 2. What's its pOH going to be? Well, we know that 2 plus X is equal to 14, so the pOH is going to be equal to 12. What I want you guys to do now is either watch this again or watch some of those animations again, and I'll link those to Schoology. And then I want you to do a little of this pH practice right here, and hopefully you grabbed a hard copy of this, but you don't necessarily have to have a hard copy. It just makes writing some of these equations easier. And I want you to do the first and second part in this. Let me know if you have any questions. I'm here in the morning, and I hope this was helpful. It was my first screencast-o-matic in a while, so sorry for the choppiness.